Thank you, Alec. I also want to take the opportunity to thank to FIC, which is my department, for organizing this wonderful conference for the 5th year in a row. Indeed, I'll talk about this topic. So let me first set the stage. So suppose you have two graphs, f and g. You can think of f as some fixed graph and g about you can think of it as some large graph, but it's not really important for the definition. We define the induced density of f in g, pfg, as follows. Suppose we take a random subset of vf vertices of vg, and we ask ourselves whether or not it induces a copy of f. Okay, so this is the induced density, and this definition naturally extends to the case where f is not just a single graph, but also a family of graphs of the same order. So we are asking ourselves whether this VF subset induces an element of the family. And of course, this is a counting question, because if we take the induced density and multiply it by the number of VF subsets, we just have a count number of the number of induced copies of F in G. So just to make sure we are on the same page, the induced density of a triangle inside the diamond, so there are two triangles and there are four subsets of size 3, so the induced density is 1/2. And just to make the point that we are talking about induced things, the induced density of this matching with two edges inside the hexagon is, well, there are 3 possibilities. We have to take opposite sides because we want induced. So it's 3 divided by the number of 4 subsets, which is 0.2. Okay, so of course we are interested in what happens in the limit. So let us first denote by IFN, the maximum possible induced density of F over all graphs with n vertices. And similarly, let us denote by IHFN the same thing, but now over all graphs G with n vertices that do not contain H as a subgraph. And many times we are interested in the case where H is a clique, and then I'll just use the notation IKFN. So for example, I3FN is the induced density over all triangle-free graphs. And one nice thing here to see is that these sequences, as a sequence of n, they are monotone, non-increasing. This is very easy exercise. So the limit of IFN and IHFN exists, and these are well-known notions. So we call these limits IF is what is called the inducibility of F. So we are asking ourselves in the limit, what is the induced density of F? And similarly, IHF is the inducibility of F over H-free graphs. Okay, so as you can guess, these are very natural questions in graph theory and extremal graph theory. So surely this has been looked at, and indeed, inducibility dates back to a classical result of Goodman, who actually proved that the inducibility of the the path with 2 edges, is 3/4. But the systematic study of this parameter and also the name inducibility was initiated by a paper of an influential paper of Pippenger and Golombik. I think Marty is here in the audience, so hi Marty, from 1975. And since then, especially in the last 2 decades, because of some machinery that was developed, there have been some very strong results on inducibility, but in general, the problem is difficult. So we don't know a lot about it. Let me just mention what we do know, some of the main results that we do know, and then I'll try to focus more on results in this talk. So the inducibility of a clique is trivial, it's just 1, And also notice the inducibility is closed under complement. So the inducibility of the empty graph is also 1. So together with Goodman's results, we have the inducibility of all graphs on 3 vertices. No more options. So what about graphs on 4 vertices? Well, here it becomes a bit difficult. The current state of the art is that we know the inducibility of almost all graphs on 4 vertices, except for one. This innocent-looking graph, P4, the path on 3 edges. We still don't know what the inducibility of this is. There are some upper bounds and lower bounds, not very far from each other, but it's still an open problem. So, okay, what about the inducibility of 5 vertex graphs? So, again, I'm not going to talk about 5, 6, etc., but I can, of course, there are more graphs on 5 vertices, and as you can see from the fact that the results are quite recent, that determining these inducibilities is not so easy. So only in 2023, the inducibility of K5 minus, namely a click on 5 vertices missing 1 edge, was determined. And similarly, K311, this 3-partite graph, complete 3-partite graph. But there are some infinite families for which we know, most notably complete bipartite graphs. This is a result of Brown and Sidorenko. And they actually determined the inducibility of KST, complete bipartite graphs. And they show that the large object, namely the graph with n vertices which maximize that, is also complete bipartite. Perhaps this is not too surprising, but the ratio of the parts is not the same as the ratio of S and T, of course. And actually, it could be irrational, this ratio. Okay. Now, I want to go back to the paper of Pippenger and Golubic, and what they observed there, there is some generic lower bound for inducibility that only depends on the number of vertices of F. So how do we do that? So let's take F and let's blow up each vertex into an independent set of size n over r, r being the number of vertices of F, and put edges between 2 independent sets that correspond to an edge in the original graph. This is the usual blow up. And as you can see, any transversal, if we pick one vertex from each part now, will induce exactly F. So this gives you many induced copies of F. But you can carry on with this inside the parts. Instead of keeping them independent sets, you can do this recursively over and over again. This is what is called the iterated blow-up. And if you do the computation in the limit, it gives you that the induced density of F is at least r factorial divided by r to the r minus r. So it only depends on the number of vertices of F. And actually, they conjectured in their paper that this should be tight for all cycles with at least 5 vertices. For the C4 and the triangle, of course, it's not tight because the C4 is there bipartite and the triangle is just a complete graph. So starting for 5 vertices, they conjectured this. Remember, they conjectured this in 1975. And it took 40 years. And this was one of the great successes of flag algebra to get an exact result to prove this conjecture for the first case, for C5. So indeed, this iterated blow-up is the best that you can do for C5. So this is the first case of the Pippenger-Golombek conjecture. And we don't know for C6 yet. On the other hand, a result of Jacob Fong's, Hao Wang, and Chungbong Li, and myself, we proved that actually for almost all graphs, let me just say what is almost, suppose I have graphs with 100 vertices, and I think of them as a random graph with 100 vertices, I just pick at random edges. And now think of R as going larger and larger, this is a typical graph. So the result says that for almost all graphs, namely the random graph on R vertices, usually attains this bound, and you cannot do better than this than this iterated blow-up construction. Okay, so this is a result. Now, we already mentioned the Goodman result, which is just the path on two vertices, on two edges, which is just K3 minus. Also K4 minus, we mentioned this with flag algebra, and K5 minus. So what more? What can we say in general about cliques missing a single edge? This is the first pressing non-trivial case. So indeed, this was solved very recently by Liu, Mubai, and Reiher. And they determined actually the inducibility of a clique missing an edge for all R. For all R. And the point is that they were able to circumvent the use of flag algebra, because flag algebra, when you come to the computational part, it only works with, you can only do things for graphs which are small. So in particular, their proof circumvents the use of flag algebra. So at least we know the induced density of complete graphs missing an edge. Or if you think about the complement, a single edge and in disconnected vertices. Also, disability of graph families is an interesting area, and let me just mention one interesting family. So take all graphs on R vertices and L edges, and ask yourself, what is the inducibility of this family? So you take at random R vertices from your host graph and ask, does it induce L edges? This is the edge statistics conjecture of Alon, Hefetz, Krivilevich, and Tyomkin. And this was solved not too long ago in some asymptotic sense by all these people that are listed here. So these are some very strong results. Okay, what about inducibility over H-free graphs? So this dates back even before the Goodman, even to 1949 for result of Zykov, and an independent proof of Erdős from 1962, where they determined the IKKR. So again, what is IKKR? I want to maximize the number of cliques of order R inside graphs that do not contain cliques of order K. K, of course, larger than R for things to make sense. So you could imagine that the best you can do is take the Turan graph with K minus 1 parts. Okay, so a complete part-type graph with K minus parts as balanced as possible. This doesn't contain KK, and one should guess that this should contain the maximum number of KRs. But it's not so easy to prove. It's not so easy to prove, and indeed the results of Zykov and Erdős prove that. Another question of Erdős, which is actually was a famous of a problem, the pentagon problem, is what is I3C5? So maximize the number of induced copies of cycles of length 5 in triangle-free graphs, I3C5. And this is another success of flag algebra, the first, even one of the early successes of it. One of the authors is Razborov himself. He invented flag algebra. And indeed, for this was solved. And the best thing you can do here is indeed take the blow-up, not the iterated blow-up, but just the blow-up itself on C5. There are also results on families of graphs in which we exclude some H subgraphs. So this is what is in the last paragraph. I don't want to get into that too much. So what is the goal in my talk? My goal is to provide a more systematic study of inducibility over H-free graphs. And the reason I want to do it is I want to take H, in some sense, I want to take H to a limit, larger and larger H, so that this will help me to get the inducibility proper without restrictions in some previously unknown cases. So what I'll do next is indeed talk about this goal. So the first thing that I would like to show you, not to show, of course, I won't be able to show anything, but tell you at least that When you get a graph, there are actually two things, there is two dichotomies. You ask yourself whether the inducibility is already reached if you exclude something, or whether to reach the inducibility you cannot allow yourself to exclude anything. Namely, is it true that the inducibility IF is already equal to some IKF, namely I'm not allowing cliques of order K, whether already that will give you the true inducibility. So let me give a definition. So we say that a graph is inducibility diverse if any limitation you put on your host graph, you will not be able to get the inducibility. Namely, for every K that you give me, IKF is less than the true inducibility. Not allowing KK limits you. Okay, so one may wonder why it's not obvious that you always don't want to limit yourselves. So of course, for cliques, this is easy. The inducibility of a clique is 1. And of course, its inducibility diverse, because once you don't allow something, the host graph cannot be a clique. So it cannot have an inducibility of 1. So complete graphs are inducibility diverse. Well, it seems perhaps one would think that dense graphs should be inducibility diverse, but this is actually false. Suppose you take a complete graph, say K100, just with one missing edge. Remember, this was covered in the result of Liu, Mubai, and Reiher, because it's a complete graph missing an edge. They actually proved that these graphs are already not inducibility diverse. There is for K100 missing an edge, there will be some point, some K, perhaps 10,000, such that if you limit yourself to not containing K 10,000, this already suffices for the inducibility. Remember I told you that almost all graphs satisfy the Pippenger-Golombik construction. So something similar happens here, but a completely different proof. Almost all graphs are indeed inducibility diverse. It's not good to restrict things if you want to get the true inducibility. So this is the theorem. I will not say anything about it, except state it. Okay, so asymptotically, almost surely, almost all graphs are inducibility diverse. So in the remaining of the talk, I want to limit myself to complete partite graphs. And this is still a very, very interesting family of graphs which we don't know much about. And more generally, I will talk about symmetrizable families of graphs. The definition will follow shortly. And this is also a well-studied topic. Of course, for example, a complete graph missing an edge is a complete partite graph, okay, for example. And it's still unresolved in most cases, despite the fact that you can pose it as a polynomial optimization problem for such graphs. The problem is that polynomials have a degree and many variables, so it's not obvious how to solve these things. Another point is that for these complete partite graphs or symmetrizable graphs, something else happens. If you want your graph to not contain some H, namely IHF, then you don't really care about H itself, you only care about its chromatic number. So IHF is the same as IKF, namely you don't allow cliques of order K, where K is just the chromatic number of H. So what are the tools? What are the tools for these things? Let me mention them. So perhaps most of you know these things. So what is a graphon, or especially in my case, a binary graphon? So a binary graphon is a symmetric measurable function from the unit square to the points 0 and 1. This is why it's binary. And how is it related to graphs? Of course, if you give me any set of V distinct points inside 0, 1, then it corresponds to an induced graph inside the graphon. How does this work? So for example, here is a graphon. Orange is 1 and white is 0. You can see that this is a symmetric measurable function. Suppose you give me 2 points inside the union interval 0, 1, say U and V. And then I'll say that UV is an edge if the value of the graphon in this point is 1. So in this example, it's not an edge. And of course, if you take now R points, for each pair in these R points, you can ask whether or not it's an edge. So this gives you some graph, and you can talk about the induced density of a graph inside the graphon. So for graph H and graphon W, the induced density is the probability that a random set of VH points in 0, 1 induces H in the graphon. I want to talk about a special type of graphon, what is called an L-step graphon or an L-partite graphon. So partition 0, 1 into L intervals of sizes x1 till xl, the intervals, and construct the following graphon, best explained by a picture. So everything is 1 except the diagonal boxes, so they are 0. So you see that this is everything it induces is always a complete partite. So this is why we call it an L-partite graphon. For example, here in this picture, this is the graphon 0.45, 0.35, and 0.2. And it's easy to see that if your graph H has chromatic number larger than the number of parts of the graphon, then W cannot contain H. For example, this cannot contain induced graphs with chromatic number 4, this example here. And why are graphons interesting to us? Because the graphon is actually a limit of a sequence of graphs. Which graphs? For example, this L-partite graphon is a sequence of complete, is the limit of a sequence of complete L-partite graphs where the nth element in the sequence is a graph with n vertices, with L parts, complete partite, where the size of the ith part is xin. Okay, so the limit of this sequence of graphs, in a well-defined sense, is this graphon. Another tool that would be useful in the proofs and also in the definition that we follow is what is called Zykov symmetrization. This, of course, relates back to the original theorem of Zykov from 1949. Suppose you have a graph F. I want to define an operation. Take 2 non-adjacent vertices, say x and y, and now let's construct another graph, F star, on the same number of vertices. So what we do is replace x with a copy of y. So this copy has adjacencies precisely like y has. And y and its copy are non-adjacent also. We call them twins. And now you can do it repeatedly. So this is called symmetrization. So we can define what is a symmetrizable family of graphs. It's a graph family that is closed under this operation. So clearly, if you take a complete partite graph and apply this operation, it doesn't change the graph. So every family of complete partite graph is symmetrizable. And it's also an easy exercise that the union and intersection of symmetrizable families is symmetrizable. But there are also non-trivial families of symmetrizable graphs. They don't have to be all complete partite. Here is an example. This family of graphs, one can check it's symmetrizable. Okay, so as I promised, for complete partite graph and symmetrizable graphs, actually we don't really care about what is H, only on the chromatic number of H. So here is the theorem. And the important part of the theorem is its second line. So suppose you have a symmetrizable family of graphs. If you don't want to remember the definition, so just think of F as being some complete partite graph. So you have some complete partite graph, and you have some graph H which you want to avoid. Then the theorem says that the inducibility of F inside H3 graph is just the same as the inducibility of F inside complete graph with order the chromatic number of H. So this means that this makes the problem more tractable because now you can do some polynomial optimization. But more importantly, the second line, moreover, the inducibility IKF, where K is the chromatic number, it's attained, it will always be attained, perhaps not uniquely, but it will always be attained by a complete L-partite graphon, the graphons that we talked earlier, where the number of parts, we don't know what the number of parts will be, but it surely will be less than the chromatic number. And of course, we don't know how much the sizes of the L partition will be, but at least we know that the limit will be some graphon of this type. So this is important. It's not such an easy theorem, but it does hold. And let me just say that the theorem is false in general for when F is not a complete partite or not a symmetrizable family. For example, it's not true when F is a C5, a cycle on 5 vertices. Okay, so again, so suppose you give me a complete partite graph F and some graph H with chromatic number K, then the theorem just says that all I have to do in the world in order to determine the inducibility of F inside K free graph or H free graph, it's the same thing by the theorem. It suffices for me to determine a point, a partition of 0, 1 into L parts, namely a point in the L-1 simplex, a dimensional simplex, where the number of parts is less than K, less than the chromatic number. And then, of course, once I have this graphon, I just can compute it. It's a polynomial, that this induced densities will just be a polynomial in X1 to the XL. And it's just now asking what is L and what are the part sizes. So this is what the problem is. And denote the optimal graphon we are looking, we want to find, but denoted by WFK. Now, it turns out that different types of complete partite graphs behave quite differently. For some graphs are inducibility diverse, some are not. In some cases, all part sizes of this optimal graphon will be equal, even if the part sizes of F are not equal. So this is the main issue. While for some others, they will all be non-equal. And I'll try to demonstrate this phenomenon in some cases. And the point is that we will be able to compute WFK as K varies to infinity, and this will mean that we can compute the inducibility proper without restriction. This will be the point. So let me just denote a complete partite graph in the usual way, K A1 till AR. A1 till AR are the part sizes. So we'll assume that they are non-increasing. Okay, and when all part sizes differ by at most one, this is what we call, of course, the Turan graph. We usually denote the Turan graph by TSR. So you have S vertices, and you want to partition them into R parts as equal as possible. So S over R floor and ceilings, and make it a complete partite graph. This is the Turan graph. Just to make sure that we are all on the same page, this is T53, which is, of course, a complete partite graph, the complete partite graph, three-partite graph, K221. So I want to go back to some of the theorems that I mentioned, but now state them in graphon language. So let's recall first the theorem of Zykov and Erdős. So remember, they determined IKKR, the inducibility of KR inside graphs which do not contain KK, and they've shown that this will be the host graph with n vertices will be the Turan graph with K-1 parts. This is the best you can do. And now I want to state it in graphon language. What does this mean when we take n to the limit? It means that the optimal constructions for KIKKR is just the balanced K-1 partite graphon with part sizes 1 over K-1. This is just restating the Zykov and Erdős result in graphon language. So of course, the next question, pressing case, would be, say, complete graphs missing an edge, which are of course two-rank graphs, right? KR minus is just the two-rank graph R minus 1, or if you will, K2 1 1 1 1 1. So let me just recap what I already said about these graphs, but in graphon language. So we started with this result of Goodman, and actually his result can be stated as saying that the inducibility of a K3 minus, or a path with two edges, is obtained in the limit by the graphon W 1/2, 1/2. Okay, so it's just this matrix with with block sizes 0, 1, 1, 0. And if you compute the induced density of K3 minus in it, it will give you 3/4, and it's the best thing you can do. So here, the number of parts of K3 minus is 2, right? It's a bipartite graph, and also the graphon is bipartite. So this might be not surprising. But let's go back to the result of Hurst. Remember, I said that it uses flag algebra, who determined K4 minus, and it's actually his extremal construction stated in graphon language that the optimal construction is the graphon with 5 parts, also equipartite, all of them the same parts. And what's interesting here? The interesting thing here is that K4 minus is only 3-partite, yet the graphon has 5 parts. And also, not all parts in K4 minus are the equal size, right? There are 2, 1, 1, but the part sizes of the optimal graphon are equal. So something interesting starts to emerge here. So this result of Pikurko, Sharif Zadeh, and Staden, they computed inducibility of K5 minus, and there you already need to take 8 parts, and again it's balanced. So it seems that something should emerge here, some pattern should emerge here. And indeed, the result, the general result for KR minus that I mentioned of Liu, Mubai, and Reiher, if you state it in graphon language, it means that it says that KR minus, the optimal construction, is the graphon with T parts, balanced, all of them of the size 1 over T, and the number of parts behaves quadratically with R, something like R squared over 2. So if you plug R equals 5, 4, and 3, you'll get the above mentioned results. And in particular, what this means is that KR minus is not inducibility diverse. For example, this means that once you forbid KT plus 1, you already have the inducibility, because already this graph, this graphon, which only has T parts, give you the inducibility. It will not make your life more difficult if you forbid KT plus 1 and above. So at some point T, you will already get the inducibility. You don't have to go to infinity to get the inducibility. So we have a complete picture of complete graphs and almost complete graphs. What about other classes of complete partite graphs? Complete bipartite graphs, for example. That's the first pressing question. I already mentioned in the beginning that Brown and Sidorenko settled it. They proved that the optimal graph with n vertices will be complete partite itself. And now if you take it to the graphon language, then KAB is attained by W alpha 1 minus alpha, so only 2 parts. And alpha is just a solution to this thing. So you see alpha could be irrational, even though any A of V are, of course, integrals. But at least we know that for bipartite graphs, the number of parts of the graphon is also 2. And it also means that complete bipartite graphs are not inducibility diverse. Even if you don't allow triangles, you don't care. The graphon already doesn't need triangles, right? It has 2 parts. So what about two-run graphs? So here the situation becomes more involved. So in the same paper of Brown and Sidorenko, they proved the following. So again, we're looking at two-run graph as vertices are parts, as equal as possible. If it so happens that S and R satisfy this weird star inequality, if this happens, then you have an answer. The optimum would be the balanced graphon with R parts, which of course also determines the restricted inducibility for these two-run graphs. But usually this doesn't happen, right? Usually this star thing doesn't happen. And another interesting anecdote in this paper is that they showed also a converse. If S over R is an integer, namely it's a totally balanced graph, K222, then they actually prove the star is necessary. If this does not hold, if star does not hold, the answer would not be the balanced partite graphon. But they didn't say what it will be, but they showed that it will not be. So for example, T126, which is K2222222, or if you will, just a matching with 6 edges, if you take the complement. So this does not satisfy star, so it will not be a 6-partite graphon at all. Okay, so the next theorem I'm going to state will actually show how we can extend the state of the art regarding two-run graphs and complete equipartite graphs and obtain a plethora of new inducibility values that were not known before. So let me state this theorem. It's not intimidating, as one might think. So theorem 3, suppose we have a two-run graph. S vertices are parts. So of course we don't want it to be a complete graph. So S is larger than R, of course, and R has at least 2 parts. Otherwise, it's trivial. So the only real restriction in this theorem is that the number of vertices is not too large. It's not more than 3R plus 1. It's not a bad restriction. For example, KR minus, S is just R plus 1. And here we allow 3R plus 1. Then the theorem tells you that you can compute. You know what happens for such two-run graphs. So if T is the largest integer which satisfies this thing, possibly it's satisfied as it's never satisfied, so then you take T equals R, then the answer, the inducibility, would be attained by the balanced graphon with T parts, 1 over T, 1 over T, 1 over T. And actually uniquely, no other thing would obtain the inducibility. And if you don't allow KL, then the answer, if you don't allow KL plus 1, where L plus 1 is less than T, then the answer would also be a balanced partite graphon. And once we know that, we can actually compute the values. This is less interesting. So we have an expression. It's best expressed by doing division with remainder of S by R with this P and Q. So we have an answer for the inducibility for these graphs. So let me give you some corollaries. Remember that the inducibility is closed for complement. So in particular, here is a case which was not more known before. Here's an infinite family. So theorem 3 determines the inducibility of all matchings and actually all graph with maximum degree 1 of any order. So example, here's a graph. This is just a matching of size 6. Notice this is the complement of the two-run graph with 12 vertices and 6 parts, each part with size 2. And this falls inside the theorem because in these graphs, we have R parts and 2 R vertices, and S is allowed to be at most 3R plus 1, so this holds for these graphs. So now we know the inducibility of every matching. And this was not known before, even for matchings of size 6 and above. So now we have it. And here's another example. What about triangle factors? again, of any order. So again, these are complements of Turan graphs, right? Because here we have the Turan graph. The complement is Turan graph with 3 R vertices and R parts. Sorry. And again, it falls into the theorem because S is allowed to be 3R in the statement. And actually, it settles the inducibility problem for all Turan graphs on at most 14 vertices. Here's some table. Let me try to make it larger. So what is this table? The left-hand columns are all Turan graphs with 14 vertices. And the right-hand column, well, it says reference. Everywhere where it's written here, this means that this follows from theorem 3 and was not known before. Column 2 is just this T from the theorem, the number of parts of the optimizing graphon, and the numerator and denominator of the corresponding value of the inducibility. Well, actually, just a couple of months ago, I think 3 months ago, a result was posted to the archive by Liu, Ma, and Zhu, which actually extended this theorem 3 and lifted the restriction of 3R plus 1. So the result claims that it should work for all Turan graphs without the restriction. I looked at the paper. Theorem seems legit. If everything holds out, and there's no reason why it shouldn't be, they actually determine the inducibility of all Turan graphs. Okay, so this is some news. The final theorem I'd like to mention, so we are leaving Turan graphs and now just looking at complete partite graphs in general. It gives a previously unknown necessary condition for a complete partite graph to be inducibility diverse or not. Namely, remember, the number of parts of the graphon, whether or not it's fixed, or maybe you have to continue to infinity. So here is the condition. Suppose you have your complete R-partite graph with part sizes A1 till AR, listed in a non-increasing order. If there is at most one singleton part, namely if AR minus 1 is larger than 1, then the theorem says that there will be some T such that the actual inducibility would be obtained by some complete T-partite graphon. Okay, we are not saying what this T will be, and we are not saying what the part sizes will be, but there will be some T. In particular, this means that it doesn't really help me to not allow KT plus 1. So this means that after T steps, we already get the right answer. So such F are not inducibility diverse. If there is only at most one singleton part, then already the true answer would be a complete T-partite graphon. And actually, this theorem is best possible because it's generally not true if you allow 2 vertex classes to be singleton. It follows from this, for a result in this Liu, Picourco, Sharif, Zadeh, and Staten paper, that K311 is actually not attained by any complete partite graphon. Okay, so here we have 2 singleton parts. So here you cannot limit anything. If you do not allow K1000 in your graph, you will still not be able to get the inducibility of K311. The optimal graphon contains all complete graphs, if you will. Okay, but perhaps, okay, so I think it will be interesting to characterize all sequences of complete partite graphs with the threshold will be 2 parts with 2 singleton parts, because, for example, for K211, which is K4 minus, we know that it's not inducibility diverse, but for K311, it is inducibility diverse. So perhaps it would be interesting to characterize the sequences for which it is and for which it isn't. But perhaps more interesting is the following consequence of theorem 3 and theorem 4 is that every to-one graph is inducibility diverse unless it's a complete graph, of course. So how does it go? Suppose you give me a to-one graph, TSR, S larger than R, of course, because not complete. So check cases. If S is less than 3R plus 1, then the theorem 3 applies. Perhaps also the Liu-Ma-Zhu theorem applies. I'm not sure if they prove that it is I'm not sure if they prove that the optimal graphon they obtained has a finite number of sizes. Maybe they did, but I don't really need it. And if S is larger than 3R plus 1, then already every part has size at least 3, so there are no singleton parts at all, so theorem 4 applies. Okay, so every complete partite graph is inducibility diverse. I thought I would have some time to say a sketch on theorem 3, but apparently I will not have. Let me just tell you what the main idea would be. Well, it is a polynomial optimization problem, but the problem is that the polynomials have high degree and there are many variables. So the thing would be to first prove that the optimal graphon must have all parts with equal size. This is the hard part, using some analytic properties of this polynomial. And once you do that, you can just use calculus to optimize the right T or the right L. So I will skip that because of lack of time. And I will switch to my final slide about some open problems. Okay, so here are some open problems in the area. The first part is perhaps difficult. It's a quantitative question to find a closed form for the inducibility of every complete partite graph. Take into account that some of the inducibilities would be irrational. Also, already in the bipartite case, some of them are irrational. So it might be not so easy to find a closed form. A seemingly easier question is a qualitative one, the second one, to characterize precisely those complete partite graphs for which the inducibility is obtained by some graphon which only has a finite number of parts, or maybe the graphon is such that it contains every complete graph. In other words, characterize the inducibility diverse complete partite graphs. This theorem 4 that I mentioned gives a partial solution, but of course doesn't give a full solution. Another question that one might ask are whether all graph inducibilities are algebraic numbers. Well, there is reason to suspect that this is not the case. Remember that we don't know the inducibility of P4, and in a recent result of mine, there is a proof where for ordered graphs, not general graphs, but for ordered graphs, the inducibility of P4 is transcendental. So perhaps this is why it's still difficult to compute the inducibility of P4. Perhaps the value is not even algebraic, which means also that flag algebra won't help you even with infinite computing power to determine the inducibility of P4. And finally, maybe it will be nice, surely it will be nice to characterize all graphs whose inducibility is this construction, the iterated blow-up of Pippinger and Golombek. Remember, we have this proof that almost all graphs, the answer is yes, but surely for one graphs, it's no. So perhaps it will be nice to give a characterization or think of it as an algorithm, given a complete partite graph, given a graph, decide whether or not it satisfies the Pippinger-Golombek bound, and this is the best you can do, or perhaps you can do better than that. Okay, I think I will stop here.